I'm Justin Song from Alibaba. I'm going to present a joint work between Alibaba and Intel. Today, myself and my brother, Edmund, so we are going to co-present. I'm going to tell a story about power capping with cloud super apps, performance, SLA protection. Power capping has been a long history, and a lot of companies using power capping to prevent power outage. However, we found maybe, as we know, maybe people just use power capping to do protection. They didn't do any performance protection to prevent undershooting. Caused performance degradation. So I'm going to show how we do that. First, I'm going to tell you about our power architecture. Here is how we use power management in our infrastructure. The blue boxes are so-called super apps. Basically, they are SaaS, PaaS, and IaaS services provided by the cloud infrastructure. And in the power and thermal resource management, and we divide this layer into two. The top half is power and thermal management on the super apps side. And the bottom half is on our platform power management side. For example, for the power and the thermal aware scheduling, our elastic compute scheduler needs to know the power consumption of each instance, and then they are going to schedule instances accordingly. That's why we divide this layer into two. Besides P and T aware scheduling, we have health management and also some notification and alarming interface. And below that layer is the engine of the power management. We have the cooling optimization, power delivery optimization, quota allocation, power budgeting, and also anomaly recovery and isolation detection. And under that is so-called physical layer. We collect data and also we do power capping. Today I'm going to show to focus on the power capping part. And below the physical layer, we have the three important elements like IDC, infrastructure, servers, and the network. And this diagram shows how we do the control. Here is a control plane. For the cooling, we do out-of-band management, and but for the power, we do in-band and also out-of-band. Basically, for the infrequent operations, we do center-to-center communication between our power resource management and app master. But for some instantaneous power management, we use local API to do very quick power management, including power capping. And this picture shows how power capping can be triggered and the conditions. If the power consumption of a rack reaches 85% for 3 minutes, then we are going to tell scheduler to do rebalance. If it reaches 100%, then we are going to stop adding new instances. And if it's 110% for 3 minutes, then we are going to do some software-based flow control. And only 120% for 5 minutes, we are going to do power capping with the performance SLA. The performance SLA definition is shown in this table. You can focus on the blue box which is performance related. We need the super apps to tell the power management what's the priority of each physical server and what of each instance, and what's the minimum frequency needed to meet the super apps quality of service SLA. We guarantee, we promised to customers. And also what's the granularity? Is per core, for memory, what's the per rank requirement, and for link, what's the link speed minimum requirement, and for DBFS, this is so-called what's the minimum performance impact if we change the frequency, not only core but also other components that we can change frequency, and also for the idle state. If we use long latency idle state, what would be the minimum latency requirement, the correlation between the latency of apps and our and the silicon long latency idle state. And we work with Intel to do the silicon level optimization. And here we have the results. On the left, we have so-called high priority instances and low priority instances. For the high priority instances, for example, like DPDK, SPDK, or maybe very important customer VMs. And for the yellow one, for the orange one, maybe they are just for shared instances or whatever, low SLA customers. If we do not guarantee any, for example, no guaranteed bandwidth or no guaranteed duration of available time, then they fall into the orange category. And this chart shows while we do the power capping, we can still meet the high priority instances performance requirement. It stays at 3 gigahertz from 135 watt all the way to 90 watts. That means we have 45 watts power capping margin that we can guarantee performance for the high priority jobs. On the right-hand side, we show as we do power capping, as time goes by, how we can prevent frequency from falling below minimum required frequency, so-called Fmin. In this example, we have 2.2 gigahertz Fmin, and in this example, we want to limit power to 250 watts. And as the power goes down, and if the frequency Fmin is hit first, then the power capping will stop, although it doesn't meet the power target. So we can prevent the undershooting during the power capping process. The undershooting can be a disaster in the latency sensitive application, especially for the database or some storage, which is microsecond sensitive super apps. Okay, next Edmund will present.
Okay, thanks, Justin. I'm Edmund from Intel. So let me quickly go through some key design. Yeah. 1 second. So let me quickly go through some key design problems for cloud efficiency design. So okay, So we can break down this problem into 3 considerations. The first one is from the CapEx side. So did we get enough return for each dollar we have invested as capital cost? So there are 2 top concerns from cloud customers on this domain. First one is rack density is low. So in Asia market, the average rack density is about 50% to 60%, and the rest of the rack space is wasted. Another one is provisional resource is underutilized. One typical case is for the power, rack power. So for example, in one of our case with customer, for one rack, for the rack with 8.8 kW power budget, the average power consumption is only about 6 to 7 kW. The second consideration is from the OpEx side. So we can also ask us for one question. Do we really need to spend so much power to get the service level objective defined performance, just like Justin mentioned for Alibaba deployment case? So the answer for most cases is also no. So today, the power, how to get the power performance proportionality at a cloud level is one key design criteria for the cloud efficiency. The third consideration is for the reliability. We need to put the infrastructure information into the orchestration system to schedule or migrate the workload when there are any failure exceptions or constraint happened in the infrastructure. So as we just discussed, the cloud efficiency design is so complex. We need to consider the energy efficiency, performance SLA, and the system reliability. We also need to consider the the different workload, like the requirement difference are for the CPU-intensive workload, memory I/O intensive workload. Also, the requirements are different from the cloud online service and offline service. Today, the computing system has supported many power and performance control capabilities. Like we are able to manage the power budget and summer margin for the platform. We can also manage the runtime frequency, either at package or core level. So we can also manage the core count and core frequency according to TDP constraint. So the fine-grained control designs can provide the flexibility to support the complex cloud efficiency solution. So this page shows a summary for Intel's solution, a solution for cloud efficiency design. So we can separate the whole data center stack into 3 layers. The top layer is a workload. The bottom layer is infrastructure and the platform capability. In the middle, the cloud OS monitors the infrastructure and manages resource. So based on the platform, based on the power and control capability provided by platform hardware and firmware, Intel closely worked with the cloud service provider to enable the innovative solution to address the cloud efficiency problem. So the power control or power capping at the group level, by pluralizing the power resource at rack level or cluster level, we are able to dynamically allocate the power budget for the server according to the resource availability at the group, seeing the rack or cluster level. So this method can help us to improve the rack density and power utilization. So turbo rack, by adding the rack battery's power capacity into the rack power pool, we can significantly improve the rack's power capacity while handling the peak power demand. This can help us further improve the rack density and the rack power utilization. So the dynamic core management can enable the cloud OS to manage the CPU or CPU cores base frequency, maximum frequency, also the power performance efficiency ratio according to the actual workload demand. This can help us to improve the overall power performance per watt efficiency at the cloud level. Hardware telemetry of any scheduling. This can help us to improve the cloud OS reliability. So also there is another layer is between the cloud OS and the infrastructure. We call the API, hardware managed API. So we see the big challenge where we deploy the cloud solution at the cloud customer side. So let us see this challenge. So look at this picture. We know the data center stack need to monitor the infrastructure and manage the resource. So we see a bunch of interoperabilities requirement at the data center, seeing the infrastructure plan and the resource plan, seeing the server management and the facility management. And also the computing system is managed by the inbound channel and outbound channel. We also needed the consistent API model across the inbound agent running at host OS and the outbound controller. And also the computer system needed to support the runtime configuration at the large scale deployment. Saying for some time we needed to control some power and performance parameter into the computing system for 100 server or 1,000 server. So here the orange box is the strawman by leverage the Redfish as a hardware management API. So of course today the Redfish is mainly focused on the server management and rack management through the outbound controller. But given Redfish the openness and the scalability, we see the potential to expand its usage to the inbound agent at the host OS side and the data center facility manager, that is at the data center wide. So by leverage Redfish API, we think it can help us to reduce the integration effort through this common hardware managed API. So let me talk about several real cases. And I'm going to talk about two cases in our cloud efficiency solution. The first case is for the power capping or power control at the group level. So as we discussed in last agenda, the power control at the group level can help us improve the rack density and the power utilization. And many of cloud customers start to deploy this solution. And in the real implementation, there are two-level controllers for the level 1 controller is a rack controller. It needs to keep timely monitors for the rack level power consumption and do the power allocation. And the level 2 controller is a node controller to monitor and manage power consumption at the node level. So based on the Redfish, we define this power control API. So there are a couple items. The first item is the power matrix. It will use to track the real-time power consumption. Another item is the power limiter. It describes the power budget information for the resource and the define the action if the power is over budget. So we can apply this similar power control policy across the node, rack, and cluster. The second case here is how to describe the redundancy information in the orchestration system. So look at the left side of this diagram. There is one rack power architecture. So look at the redundancy. There are 5 redundancies. It's very complex. Power source, PSU in the rack, BBU in the BBS. So based on the Redfish, we can simplify the redundancy definition as left side mockup. The first redundancy is power source. Generally, we have 2 power feed for one rack, feed A or feed B, and they are sharing the loading. The second redundancy is PSU in the power shelf. They are sharing the loading. And the third redundancy is BBU, is a battery unit cell in the BBS system, and they are also sharing the loading. The fourth redundancy is between the BBS and the power source. In case there are both feed of the power source is filled, the BBS will take over. take over, so they are fail over. And the last redundancy is BBS and the PSU in the power shelf. In case this is especially for the peak shaving with the rack battery system. In case the power consumption is over the rack power budget, the BBS will share the loading together with the PSU. So we can see based on the Redfish mockup, it's more clear for the orchestration system to understand the redundancy information for each specific node in real time. So we believe the Redfish-based API can help us to address the common hardware managed API problem in the data center stack. So call to action. So performance SLA-driven power optimization is very critical for the TCO and the PoE efficiency. We need a platform and a solution co-innovation to support the dynamic, flexible, and workload in awareness optimization solution. And open and standard API are able to reduce the deployment cost in the large scale data center. We need a collaboration to define the common telemetry and control interface for OCP platform. Maybe we can leverage the ongoing effort for baseline OCP hardware managed profile. And the cloud developer and users need to understand and define the performance requirement based on their cloud applications. And let's get involved into the hardware management project in OCP. Yeah. So, yeah. That's my presentation. Any question? Yeah. Yeah. Go ahead.
Yeah. Can you go back to the first half of the slide, the example with the two graphs? The last, yeah, that one, the second one. Next one. So a couple of questions. First is, do you mean in your use case, you over-provision a rack, meaning you put more servers that exceed the peak power capacity a rack can support? Because in your algorithm to power cap the thing, you change from 80%, 90%, 100%, 110%, right? Does it mean that you put more servers than the rack can actually support at a full peak capacity?
Yeah, we did.
Okay. You did. How much over provision that you do?
It's hard to predict because you have to use to run multiple super apps on the same hardware. You cannot always run the same kind of super apps.
So you mean for each workload, you have different over provision factors. For example, for workload A, you over provision by 10%, B by 15%. You benchmark them.
So the cloud workload is almost impossible to predict.
Right, exactly. And then how do you figure out the exact amount of server to put into each rack?
Actually, we use flexible rack. We manage power by I/O, not only by rack. That means we calculate the aggregate power for the whole I/O. Maybe
Okay,
20, 30 racks per I/O.
I see.
Then you'll have a bigger pool of power.
I see. So the pool that you can have is on the units is actually per I/O, not per rack. So you have the per I/O budget instead of a per rack budget, so that you can.
For the scheduler, they still need to have a upper limit per rack.
Yeah.
So
There. Yeah. Then.
divide the whole capacity of the I/O by the number of racks.
Right.
That's the upper limit. It's a sum limit to scheduler.
So there is no hard limit to the breaker to the single rack.
There is a hard breaker for the I/O, but
Not for the rack.
but not for the rack.
Okay.
Even for the I/O, it's never hard in the analog world. If you look at the curve of the breaker tripping, it's
Mm-hmm.
So you need to know when you may look at specific parts to understand the behavior. Also, you need to understand the thermal cooling capability.
Yeah, yeah.
If your cooling capability can be enough more than your power to compensate, it's okay.
Okay.
Usually it's okay.
Yeah, I guess I can follow up with you offline about this because we're really interested. But the second question is on your example here. You mentioned that on the same node, you have different processes running on different CPUs. So you basically send a command to your node manager capping the CPU power to a certain voltage. And how do you make sure that like the blue line actually runs on a CPU that has a higher frequency, and then the yellow line on the other CPU that...
Today, node manager doesn't have the full core control capability.
Right, and then how do you achieve this?
So we do not go to out-of-band to do this kind of control.
Okay.
We use the in-band control.
So you write the MSRs to the RAPL, and is it how you do it, or?
Yeah, we could use RAPL interface and also WP interface.
Okay.
Also, as I said, we need to interact with scheduler to understand the requirement from the supervisor.
Yeah, but I'm still confused. How do you control the frequency, or do you control the frequency at all? So if say for example, you have 2 threads or 2 processes running on 2 CPUs. How do you control the frequency on one thread to be, say, constant, and then the other thread to be like gradually decrease over time?
Power takes priority. Power is number 1 priority, and the second is frequency. So we use power interface first, and followed by interface. The frequency.
Then how do you control the frequency? So you just cap the frequency on a particular CPU? Is that how you do it?
Power domain right now, for example, on SLA is per socket. There is no standard granularity power.
Right.
Have the power budget per socket, and then we use frequency control now to do the performance.
So basically you change the frequency on the core that runs a low priority job, and then you match it back to your power reading from, say, BMC or platform, and to see whether you meet your budget or not, right?
Yeah.
Okay, all right, cool. So you're now using a node manager, actually, basically.
Node manager doesn't have this capability.
Right, right.
It always has undershooting. Yeah. Also, the fluctuation time before.
Yeah, I think, so in my experience, if you control by frequency, you kind of cannot have a very hard SLA to say you need to cap to a certain power by a certain time. Do you have a problem in that when you in your actual application? Say, for example, you have a hard limit to hit by a certain time, say it's 10 seconds or 30 seconds, and then by just controlling the frequency, you cannot achieve that sometimes.
Frequency here changes in no time, in like maybe just a couple of milliseconds. So, and also we do the workload replication. Before we deploy workload, we do offline characterization to make sure we can recognize the possible workload patterns. If we can use a signature to know that maybe a specific workload pattern shows up, then we know what frequency could be the best fit for that pattern.
Okay, and the last question is, since it's OCP, is any of the code going to be open source?
As Edmund and John, we are going to work on the Redfish profile, as I understood.
But this part, the real meat of the thing, is not going to be open sourced. Only the Redfish interface.
I think we are going to be, we need to be educated so to understand how,
Oh,
yeah, how we work with hardware management. Sorry.
Okay, all right, cool.
Maybe is a recommended project or OpenBMC project or either OpenBMC project. But there's still a lot of issues there because there's something related to Alibaba's contributor related to internal contribution. We need to address those opens before we make sure it can be open source.
Just curious, how much over provision can you achieve in general? Do you have a rough number?
So in the interest of time, it's 4:30. So feel free to continue your presentation. I just want to thank the speakers before we end here. So thank you.